Hi everybody, this video covers section 3 of chapter 1 and we will be talking about complex numbers. First we're going to introduce the concept of a complex number and go over some basics. We are going to talk about the basic operations of complex numbers, namely addition and subtraction, multiplication, and division with the use of this thing called a complex conjugate. And then we are going to talk about the periodic nature of I, which happens to be equal to the square root of -1. All right, so let's take a look at this equation. We have x squared is equal to -1. The first question is, can anybody think of a real number that makes this equation true? Well, the answer is no, there is no real number, because any real number that you take, if you square it, it becomes a positive number. So there is no real valued solution to this particular equation. Okay, so here's what we can do. If there's no real valued solution, hey, we can make a solution up. And how can we do that? Well, the mathematical technique is called extending the field. And how do we extend the field? Well, we create a number. We give it a name. How about we call it I? Okay, and we will say that I squared is equal to -1. Well, if I squared is indeed equal to -1, then I must be equal to the square root of that, or the square root of -1. We call that number I the imaginary number. Okay, so let's let A and B be real numbers. Then the sum A plus B times I is what we call the complex number, where A is the real part and B is the imaginary part. And also, this representation right here is what we call the standard form of the imaginary number. And in most of your homework problems, you're going to be asked to express your answer in this particular form. Some number plus some other number times I. Okay, so once again, this is the standard form. It's also known as the Cartesian form. There is also another form for the complex number, and that happens to be what we call the polar form, where x is equal to r times e to the I theta. Here, r is actually the magnitude of the complex number, and theta is known as the phase of the complex number. Okay, now, as I mentioned, the complex number, the field, or the set of all complex numbers, is actually what we call an extension of the set of all real numbers. By introducing I, we have a whole variety, we have created a rather large extension of the complex number. Now, what does this mean to you? Well, what this basically means to you is that every single number that you have dealt with up until now has been a complex number. However, it's been the complex number where the case where b is equal to 0. Now we're not letting b, now b is not equal to 0, and of course now it includes a whole another class of numbers to include purely imaginary numbers. But basically, every number is a complex number. The set of all real numbers is a subset of the set of complex numbers. First thing that we're going to need to do is talk about how to express complex numbers, or how to write each number as a product of a real number times I. And here we have the square root of -48. Okay, so how do we write this? Well, we can rewrite the square root of -48 as the square root of -1 times the square root of 48. Square root of -1 is I. So whenever you see a negative, replace it by an I, and then you have a positive square root. Now we need to see if 48 has any factors that are perfect squares. And what we do is we start off with the largest perfect square that's less than 48, which would be 36. And obviously that is not a factor of 48. Neither is 25, the next perfect square, 5 squared. That also is not a factor of 48, but 16 is. Indeed, 16 times 3 is 48. So we can write this as I times the square root of 16 times 3, which would be equal to I times the square root of 16 times the square root of 3, and then this will be I times 4 times the square root of 3. And there we go. We're done. Okay, one of the things you need to point out, one of the things which is important to point out is to understand that the square root symbol is actually a grouping symbol. This radical is nothing more than a different way to write negative a raised to the 1/2 power. As a consequence, you need to evaluate what's inside here first before you evaluate the entire thing. For example, well, let's go ahead and just skip that. Let's do it. Let's use this as an example. For example, this is one thing you cannot do. You cannot take negative 3 times negative 12 and rewrite this as negative 3 times 12, or negative 3 times negative 12. That would give you the square root of positive 36, which would be equal to 6. This is wrong. Don't do it. Instead, you would do it like this. This would be equal to I times the square root of 3 times I times the square root of 12. Okay. Then you can multiply the i's together, get negative 1. And then you would have the square root of 36. And yes, you would get negative 6. This is correct. So once again, you want to evaluate this to get I times root 3. And you would want to evaluate this term to get I times root 12. Okay, here's another one. Once again, we want to evaluate the square root first. And in this particular case, you would have, well, let's do it explicitly. Negative 1 times 20 over here. The square root of negative 1 times 2. The square root of negative 1 is I, so we have an I over here. No, not a negative I. We have I times the square root of 20 divided by I times the square root of 2. Now the i's cancel. That's pretty cool. But we have a radical term in the denominator, and we need to rationalize the denominator, and we can do that by multiplying both sides or multiplying top and bottom by the value of the denominator. So we're going to multiply this by square root of 2 divided by the square root of 2. If we do, we are going to have the square root of 40 divided by 2. Okay, and then we need to see if there is a perfect square that's a factor of 40. Of course, 36 is not, 25 is not, 16 is not, 9 is not, but 4 is. So we can rewrite this as the square root of 4 times the square root of 10, because if 4 is a factor, then 10 is the other factor, divided by 2. This would be equal to 2 divided by 2 times the square root of 10, which of course is equal to the square root of 10. So that's how you would do that. Once again, remember, you want to evaluate this before you move on, or before you combine. Okay, now here we want to write this equation in standard form. Now remember, standard form is going to be a, one number, plus some other number times I. And we have a negative square root, so we're going to have an I in here somewhere. Now the first thing that we can do is we can write this as negative 8 over 4 plus the square root of negative 128 divided by 4. Okay? Negative 8 over 4 is just negative 2. Okay? Plus, now the negative sign, we can replace that with an I, and then we will have the square root of 128 over 4. And now this is in standard form, but you will also need to simplify this, which basically amounts to evaluating this square root. Now notice that what are the perfect squares that are factors of 120? What are the perfect squares that are less than 128? Well, there's 11 squared, which is 121. There's 10 squared, which is 100. There's 9 squared, which is 81. There is 8 squared, which is 64. 4. And 64 times 2 is 128. So we can rewrite this as negative 2 plus I times the square root of 64 times 2 over 4. Okay, well, the square root of 64 is 8, so this will be negative 2 plus I times 8 times the square root of 2 over 4. And then notice that 8 divided by 4, well, that's just 2, and that gives us our final answer, which will be negative 2 plus I times 2 times the square root of 2. And that would be in standard form. You could also write this as negative 2 plus 2 root 2 times I. That's probably better. I just like to keep this away from the radicals so there's no confusion there. Okay, so now we want to talk about basic operations of complex numbers, and that would include addition and subtraction. Now, when you add and subtract complex numbers, you have to treat the real parts and the imaginary parts separately. They cannot combine, at least in terms of addition and subtraction. Okay? So suppose you have two numbers. One is a plus bi, the other one is c plus di. How does the addition and subtraction work? Well, you add the real parts, a and c, or you subtract your real parts, a and c, to get your new real part, and then you add the imaginary parts, b and d, or subtract them depending on what you're doing, to get your new imaginary part. So for addition, you will have a plus c, and then for the imaginary part, you have b plus d, and then for subtraction, you would have a minus c, and then for the imaginary part, you would have b minus d. Okay, so let's see how that works in a couple of examples. Here's our first one. We want to find the sum of 3 minus 4i plus negative 2 plus xi, and we want to express the answer in standard form. Okay, once again, we're going to add the real parts. That's going to be 3 plus negative 2, 3 plus negative 2. I should have a bracket there. Plus times I, and now we're going to add the imaginary parts, which will be negative 4 plus 6. Okay, and then 3 plus negative 2, well, that's 3 minus 2, that is 1. 6 minus 4 is 2, so this is going to be 1 plus 2 times I. And there you go, you're done. Okay, what about the next one? Well, oh, there's the solutions. I forgot about those. Well, here's the next one. And once again, for this one, we are going to subtract the imaginary parts and then subtract the real parts. So we are going to have, well, the negative 4 minus 6. Actually, that was there we go. Negative 4 minus 6, that's our real part, plus I, and then it's going to be 3 minus a negative 7. Negative 4 minus 6, negative 4 minus 6, plus I, always plus I over here. Then we have a 3 minus negative 7. And what do you get? Well, negative 4 minus 6 is negative 10. Plus 3 minus negative 7. Well, this is basically 3 plus 7, because when you subtract a negative number, it's just like addition. So this is 10 times I. And that would be your answer, which once again is right there. So that pretty much is addition and subtraction of complex numbers. And in a nutshell, basically we add the real parts together and we add the imaginary parts together, or we subtract the real parts together and the imaginary parts. What about multiplication? Well, if you've noticed, if you were multiplying two complex numbers, let me see if I can do it over here so I don't screw up my graphics, we would have a plus bi times c plus di. And look what we have here. We basically have two binomials. So we multiply these two together like we multiply any other two binomials, taking advantage of the fact that I times I is equal to negative 1. So this is what we do. Well, here are our two binomials. We multiply the first, AC. We multiply the outer, A times DI, IAD. Airport in Washington, Dulles Airport. Inner, BI times C, that's IBC. And then finally, we multiply the last, which is BI times DI, which is I squared BD, but I squared is equal to -1. So this right here is a real number. And when we combine the real parts to the imaginary parts to get our standard form, we will have AC minus BD plus I times AD minus BC. Now, do I expect you to memorize this? Gosh, no, that would be absurd. I do expect you to understand how to do FOIL and also understand this property of a complex number. So with that in mind, let's take a look at this particular problem right here. Here, once again, we are going to do FOIL. And this is what we're going to have. We're going to multiply the first together. That's going to give me 6. We are going to multiply the outer together. That's going to give me 8i plus 8i. We're going to multiply the inner together. That will give me 9i plus 9i. And if we multiply the last, we will get plus 12i squared. But I squared is equal to -1. So this becomes 6 plus 8i plus 9i minus 12. And then now we can combine the real parts and the imaginary parts. 6 minus 12 is -6. 8i plus 9i is 17i. And there is our answer in standard form. Okay, let's do one other number. For the second problem, we have 6 plus 5i times 6 minus 5i. So we just go ahead and use FOIL again. 6 times 6 is 36. 6 times -5i, that's -30i. 5i times 6, well, that's positive 30i. Well, isn't that convenient? And then finally, 5i times -5i is, well, 5 times -5 is -25, and then I times I is I squared. Okay, now notice here, we have -30 here, 30i here, and positive 30i here. They cancel. So now we have 36 minus 25 times I squared. Well, I squared is equal to -1, so that becomes 36 plus 25, and that is equal to 61. But notice here that we can write 36 as 6 squared. We can write 25 as 5 squared. So what do we have? We have that when you have a problem like this, 6 plus 5i times 6 minus 5i, the answer is going to be equal to the square of the real part plus the square of the imaginary part. And it doesn't really matter which one, because the square of 5 is 25 and the square of -5 is still 25. And this actually is a very special pair of numbers. We actually call this the complex conjugate pair. And is very handy in a number of operations in complex numbers, particularly the area of division. But notice what happens when you multiply a complex number by its conjugate. What you get is a real number, and that real number is equal to the square of the real part plus the square of the imaginary part. So let's talk a little bit more about complex numbers or conjugates. Actually, I think I said everything there is to need to say about it. Okay, complex conjugate pairs are two numbers which have the exact same real part but opposite imaginary parts. So they have the form a plus bi and then a minus bi. They have a couple of properties in addition. One is if you add them together, you get a real number, a purely real number, and its value is equal to 2a. If you subtract them, you get a purely imaginary number, and the value is equal to 2bi. But the most important property is this, and this is the property that I want you to pay attention to. It's multiplication. And that is that if you have a complex number multiplied by its complex conjugate, you are going to then the answer is going to be the square of the real part plus the square of the imaginary part. And once again, these are useful when you are dividing complex numbers, which brings us to our next problem. And this is write each quotient and express your answer in standard form. Let me do this up here. So here we have 3 plus 2i divided by 5 minus I. And we want to somehow get this into the form of some number plus some other number times I. Well, to do that, we need to get rid of this complex thing in the bottom. How do we get rid of that complex thing in the bottom? We'll call it, we multiply this by 1, where the numerator is the complex conjugate of 5 minus I, which will be 5 plus I. And the denominator is also the complex conjugate of 5 minus I, which is 5 plus I. Okay, now, here, in the denominator, we are multiplying two complex conjugates together. And the answer is going to be the square of the real part, which is 25, plus the square of the imaginary part, and the imaginary part is -1, square it, you get 1. And that's the denominator, which of course will be 26. Now for the numerator, we have to go ahead and FOIL, and we will have 15, 3 times 5, plus 3i, plus 10i, 2i times 5, plus 2i squared. Okay, this will reduce to, in the denominator, we have 26. This right here is basically -2 because I squared is -1. So we have 15 minus 2, which is 13. Then we have 3i plus 10i, which is 13i. Okay, we can go ahead and now write this in standard form. This will be 13 divided by 26 plus 13 divided by 26 times I. Okay, and of course these can be reduced, and when you reduce them, you will have 1/2 plus 1/2 I, and that will be your answer in standard form. Okay, what about this one? Well, this one, we are basically taking 3 and we're dividing by I. But once again, we just need to write, we want to multiply this by a fraction where the numerator and denominator is the complex conjugate of I. Well, what is the complex conjugate of I? Well, remember, the complex conjugate of A plus BI is A minus BI. So in this case, the complex conjugate of I is just -I, because we have an implied coefficient of 1. So we're going to multiply both numerator and denominator by -I. So over here, we would have basically, over here we have the real part squared, which is 0, plus the imaginary part squared, which is 1. So we are going to have 1. And then over here, we have -3i. And so, -3i, sorry. And so our answer is going to be -3i. And this kind of brings up one property of complex numbers, which is if you take any number, any real number, divide it by I, your answer is going to be -ai. Now we want to talk about the periodic nature of complex numbers. So we have here that I to the first power, of course, is equal to I. I squared is I times I, which is -1. I cubed, well, that's just basically I squared, which is -1 times I, which is -I. And then I to the fourth is I squared times I squared, -1 times -1, or I. And then when we get to I to the fifth, it repeats, because that's I to the fourth, which is 1, times I, which is I. And of course, we could continue the cycle. I to the sixth is -1, I to the seventh is -I, and of course, I to the eighth is 4. And notice that the powers of I are periodic with period 4. And with that, we can use that property to simplify each power of I. Okay, and the objective here is to take whatever power that is and convert it to either I to the 0th power, which is currently 1, I to the first, I to the second, or I to the third. So let's take a look at I to the 203. We want to simplify this. And how could we do this? Well, one of the ways that you can do this is take 203, divide it by 4, and find the positive remainder. So if we took 203, divided it by 4, you would get 50, and you would have a remainder of 3. Okay, another way of looking at that is that 203 is equal to 4 times 50 plus 3. And another way of looking at this is if you actually used your calculator, you would do 203 divided by 4. That would give you 50.75. Multiply your 0.75 by 4, you get 3. But anyways, that all basically comes down to show you that this will be equal to I cubed, which is negative I. Okay, so I to the 203rd power is equal to negative I. Okay, and this right here actually is our last example. What about I to the negative 7th? Well, for something like this, there's a couple of ways that you could do this. The first one is, well, you can just keep on adding 4 to it. I to the negative 7 is equal to I to the negative 7 plus 4, which is I to the negative 3. All right, well, that's also equal to I to the negative 3 plus 4, which is equal to I. Okay, so that's one way. Another way to do this is you can actually divide negative 7 or divide negative 7 by 4 and find your positive remainder. So here's negative 7, here is 4. If I do 4 times 2, or 4 times negative 2, I will get negative 8. Then when I change the sign and add to my long division, I will have a remainder of 1. And there you go. The other thing that you can do is in your calculator, you can do negative 7 divided by 4. If you do, you will get negative 1.75. We don't care about the negative 1, we care about the negative 0.75. Add 1 to that. Okay, that's going to give you your, we can't work with negative decimals, but we can work with positive decimals. And that will give me 0.25. That's I to the, that is basically a remainder of, that's basically a remainder of 1. So this corresponds to I. So we would have that I to the negative 7th is equal to I. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.